Hi everyone. In this lecture, we'll start with the discussion of digital communications. What was the motivation behind digital communications? So, if you recall in the history lecture that I gave in the first two lectures in in wireless communications, I discussed one of the first inventions which put the full power of communications into applications. Of course, was the radio, that was the wireless communications, but the theory of communications was properly developed for telephones. So long distance telephone was a big problem until they invented amplifiers. So around 1910, the amplifiers were invented, and vacuum tube amplifiers were first vacuum tube amplifiers were invented. So they could actually start having intelligible long distance telephone conversations. So what they did was that you have a sender, from a sender somebody sends the signal. Then there was something called as a repeater, because once your signal was traveling for longer distances, it was getting attenuated. So someone had to amplify it again. So a repeater essentially is an amplifier. Again, it was transmitted through a wire, and again it was amplified, and so on. So the signal level was sufficient. When it reached the receiver, it was sufficient for the the receiver to actually hear an intelligible conversation, okay, or intelligible speech. So let's say there was no receiver, then the sender signal would have completely decayed down. By the time it received the receiver, you would not have received any signal at all, any message signal at all. Okay, you would be receiving only the noise of the wires, which the metal wires, where the conducting wires, they all exhibit noise. So that's what you would be listening. So to solve that problem, amplifiers was the best solution. In fact, Bell Labs famously called the vacuum tubes as the Aladdin's lamp, the electric lamps. They called them the lamps, okay, and the magic lamps. And they say that because of that we could solve it. Essentially, what they did was they just amplified your signals at regular intervals. Now, what we'll do is we'll try to write a mathematical model. I'm having a signal here. Of course, every time you generate a signal, there is always noise going to be associated with it. So a signal, for example, a sender uses a piezoelectric crystal to convert message signals to electrical signals. The process of conversion itself can be noisy. There may be some noise associated with it. So we define a term called signal to noise ratio, S by N. That is the signal power divided by the noise power. And we'll see what happens to the signal to noise ratio as it propagates through this chain. So to understand that, what I'm going to do is first I'm going to divide this into two parts. The repeater actually contains of two sections. There is a wire and there is an amplifier. Okay. Any wire, because it's a conducting wire, which it has a finite capacitance with respect to a ground plane. It can, for example, I took an example of a coaxial cable. Telephone wires uses twisted pair cables. A coaxial cable can be seen where this is your central conducting wire cable, and this will be your metal cable which is surrounding that, which is the ground cable. So as I discussed in the class, there will be it's like two capacitors wound, two metal plates surrounded by a dielectric in between. So that gives you a capacitor, and the conductor itself has a finite resistance. So I said that in the class that we can model this RC, the distributed RC network, as a simple lumped RC model. And any RC circuit, we said it's like a low pass filter with a pole given by 1 by RC. I mean 1 by 2 pi RC in hertz. So this is like, this is called, I can call it as a channel. So this is the medium through which your signal is propagating. Now you cannot send a signal greater than the channel bandwidth within this. Okay, we will revisit this parameter once we talk about Shannon's information theory, information capacity models. Okay. So the bottom point is that a resistor, a channel wire, the channel in which it is going can be modeled as a low pass filter, and anything that is conducting and has some resistor associated with it will have some noise. So if I'm going to launch a signal at the input with a certain signal to noise ratio, the signal is there, noise is also there. At the output, because a low pass filter, the DC gain, only DC there is gain is 1 for a low pass filter. For any other frequency, there will always be a slight attenuation in the signal. So signal will be slightly attenuated, but you are going to add new noise through the resistor. The resistor itself is going to add new noise. So which means your noise will be slightly higher than what it was at the input. So what happens to the signal to noise ratio at the output is going to be smaller than the signal to noise ratio at the input, because signal will see attenuation and there is new noise being added. So let's say the old noise also saw the attenuation, but I'm going to call it Ni as the new noise that this wire is going to add. Okay. So now if you see the overall signal to noise ratio is definitely, previously it was simply S by N. This number is going to be less than S by N. S by N is going to be greater. So I'm going to call it SNR at the output, which is at the RC filter output, is going to be smaller than the SNR at the input. and by a factor alpha. I'm just using a proportionality factor alpha, and alpha is less than 1. Similarly, the next thing we'll model is an amplifier. Repeater is an amplifier. So an amplifier can be modeled as an amplifying circuit, as an amplifying element with an additive noise to it. Now your signal and noise both are fed to this. So signal, usually I should have used the, I'm sorry, in the previous discussion I just used alpha as a gain, but here we are all usually, when noise, we talk about powers. So when I multiply, I should multiply by gain square. So I'll get this. If I ask you to find the signal power at the output, it will be simply a square times s. S is the signal power at the input. The noise power, if it was purely a noiseless system, it's going to be a square times n. So the signal to noise ratio at the output is also going to remain the same if the amplifier is noiseless. But at this point, I'm going to model the noise of this amplifier as, say, N0 or NA. Let's call it NA. So what's going to happen at this point is the signal to noise ratio is going to be a square n is the input noise plus NA. So now if you see again, your signal to noise ratio at the output is going to be smaller. So I'm going to call Sn at the output as beta times Sn at the input, signal to noise ratio at the input, where beta is less than 1. Right? There is more noise, therefore, than at the input, therefore signal to noise ratio will degrade. So now if you see, the overall signal to noise ratio with a wire and a repeater can be modeled as the output signal to noise ratio will be simply alpha into beta times the input signal to noise ratio. Now since both alpha and beta are less than 1, alpha beta itself is going to be less than 1. The product will also be definitely less than 1. Now if I cascade n such stages, at each stage, by the time this is the signal to noise ratio at the sender, I am going to call Sn by S. By the time it reaches the receiver, it would have gone through n stages, and at each stage your signal to noise ratio is going to reduce. Now since this is less than number, alpha beta is the term which is less than 1, power n, as n tends to infinity, this term will tend to 0. Which means if your n is very, very large, if you have many, many repeaters, eventually you will not receive any signal at all. Your signal power will become 0, you will have only noise. So that's the problem. So that is the problem with analog communication systems. If this was actually analog telephony, they used to transmit analog signals, amplify using analog amplifiers, and transmit it at the receiver. Okay, and transmit it and receive at the receiver using an analog circuitry. The problem with analog circuitry and analog transmission was noise. Okay, fundamentally, because of the presence of noise, eventually your signal to noise ratio, if you add many, many repeaters, it's going to decay down. So they had to think of some better solutions of solving this problem. Okay, so this was the, now what they thought was that, okay, what they thought was, how do I better improve, make long distance signal transmission possible? The only way they thought was just increase the signal to noise ratio at the input. So just keep increasing more and more signal power, more and more signal power. But after a point it looks silly, it's almost impractical. You can't keep increasing it indefinitely. So is there some other way to fix it? With a finite signal power, at still I can have very low, very good SNR at the receiver. That's when the idea was thought during engineers at Bell Lab. There was Hartley, there was Nyquist, there was Shannon. So all of them thought of this idea. It was an idea, generally agreed upon by many engineers at that time. Was instead of transmitting, analog signal has infinite possibilities. So that's why we have to faithfully amplify it. Instead of that, if I somehow convert this analog signal to a finite level of values, to a set of finite values, then I know exactly what these finite values are. Okay, so I think I'll discuss quickly. I'll discuss this next part in the next class about digital modulation.